If you are given a quadratic function within a word problem, it's important that you read the problem carefully, and then you decide what problem is going to be maximized or minimized. Most of your parabola problems are going to be a maximum or minimum problem. So use those conditions to make sure that you are creating a function. Maybe you'll have to create that function yourself. So that's usually the first step, is create your function. Maybe the function's given to you. Who knows? Make sure that when you do write it, you write it in standard form, and then calculate your vertex. Right, so if we find the h value of the vertex, and we know that a is positive or negative, that will tell us whether it's a maximum or minimum, and then we can plug it in and find out. So every problem is going to be a little bit different. There's no one size fits all. It's just a matter of you taking the problem and then going and working with it. So let's just jump right in and do a couple of examples. So say you have 120 feet of fencing to enclose a rectangular region. All right, I stop right there and I think about what the problem is telling me. So it says I have a rectangular region. So I'm a picture person. So I'm going to draw a picture of a rectangle because that's what I have. And then I'm going to write down what I know about it. Now it tells me that I have fencing, which means I have a perimeter, right? So what is the formula for the perimeter of a rectangle? A perimeter is 2 lengths plus 2 widths. And they told me what the perimeter was. I have 120 feet. So instead of perimeter, I'm going to put 120 feet. And I get this equation, which I can simplify because everything here is divisible by 2. So I get 60 equals L plus W. Okay, so that's what the first sentence tells me. Then I'm going to move to the second sentence and think about what it tells me. The second sentence says, find the dimensions of a rectangle that maximize, so that's important, the enclosed area. So what is the area of a rectangle? The area is length times widths, and that's what we want to maximize. So that is going to be my quadratic function. But you may be asking yourself, how is it a quadratic? This is how. Instead of L or W, we need to do a substitution so that we get all one variable, because that's what we absolutely have to have. We have to have one variable. I decided to put this to solve for the length. So length equals 60 minus W. So instead of L, I'm going to put 60 minus W multiplied by W. So if I simplify that out, that gives me 60W minus W squared. And if you want to write that in function notation, my area in terms of the width is negative W squared plus 60W. I wrote it in standard form because that is going to help me find the vertex. So they already told me it's a maximized problem, so that already gives me a hint that I need to find the vertex of this parabola. So my A value is equal to -1, and my B value is equal to 60. So x equals negative b, which is negative 60, over 2 times -1. So negative 60 divided by -2 is positive 30. So I know the maximum occurs when the width, so again, we didn't do x, we did w, right? So the width is 30 feet. So I know the width for my maximum area, so the maximum area is going to occur when your width is equal to 30 feet. Now, if you want to, you can just plug that 30 into your area function, and that will give you the area. However, I'm a little lazy, so I'm going to take this width, and I'm going to go over here, and I'm going to plug it in right here to find the length. The length is 60 minus 30, which would also be 30. So the length is going to be 30 feet when that maximum happens. Well, what is 30 feet times 30 feet? Because that is the area of a rectangle, right? 30 times 30. So my area is going to be maximized at 30 times 30, which is 900. So 900 feet squared. So, but again, if you want to, you can also just plug it into your equation, which is negative 30 squared plus 60 times 30. And guess what? You're going to get 900. So either way you do it, you will end up with the same answer. It doesn't really matter which way. Some instructors may want you to plug it back into the function to show that you're actually finding the parabola. Some may not. So it just depends. I would listen to their instructions and tell you how they want you to do it, but you can do it either way. Both are totally adequate. All right, so here's an example exactly like this one for you to try. The only thing I did was I changed the amount of fencing. So press pause and please give this one a try. All right, so we're going to approach this one the same way. We are starting with a rectangular region. Our perimeter this time is 200 feet. So 200 equals 2L plus 2W. Again, I can simplify that. We want to maximize the area. So the area of a rectangle is length times width. I am going to do some kind of, whether you want to solve for L or W, it doesn't matter. I think I solve for W this time. So W equals 100 minus L. So I plug that into my function. So it's going to be L times 100 minus L, which gives me 100L minus L squared. So if I write that in function notation, my area in terms of the length is negative L squared plus 100L. My A value is negative, which means my parabola is pointing downwards, obviously, which means my vertex will be a maximum. So that all makes sense. I need to find this vertex now. So x equals, so again, I didn't solve for x, I solved for L, so let's write that. L equals negative b over 2a. So negative 100 over 2 times negative 1, which would be negative 100 over negative 2, which is positive 50. So the maximum is occurring when the length equals 50 feet. And so if you want to, you can find the area by plugging in 50 into the function, or if you're like me, a little lazy, I'm going to plug that in over here, and that's going to tell me that the width is also 50. And the area would be 50 times 50, which is 2,500 feet squared. That is my maximum area. And again, if you plug it into your function, which would give you negative 50 squared plus 100 times 50, you will also get 2,500 feet squared. So again, it doesn't matter which way you do it, you should get the same answer. All right, there are variations of this same problem. They're not always going to be the same. You might be saying to yourself, well, both of these equations gave us squares. The last one was 30 by 30, and this one's 50 by 50. So is it going to be any different? Yes, the answer is yes. So if you have this situation where you have 120 feet of fencing to enclose the rectangular region along a river, so you don't need that fourth side, you just need the 3 sides. I have labeled the sides according to what they will need. So these sides will both be x, and this side will be 120 minus 2x with that 120 feet of fencing. So find the dimensions of the rectangle that maximize the enclosed area this time. So this time your area is going to be x times 120 minus 2x. So notice a slightly different equation than last time. So if we write that in standard form, it's negative 2x squared plus 120x. So there is my area function. And then I can do the same thing. Find your vertex. So this time when I find my vertex, my x value is going to be negative 120 over 2 times negative 2, which is negative 120 divided by negative 4, which is positive 30. So the x value here is going to be 30 feet. And then if you want to find this value, just plug in the 30 as well. So 120 minus 60 is 60 feet. So there's the dimensions of my rectangle. And again, if you multiply those two, you would get 1,800 feet squared. So that's going to be your maximum area. However, you can also plug it into the area function. So if you take that 30, plug it into the area function, you would also get the same value of 1,800 feet squared. So again, you will get that. Again, just make sure that you solve this the way your instructor would like it to happen. I'm pretty relaxed, and so I don't care either way, but make sure that you just listen to what your instructor tells you. All right, so here's an example just like this one right here. I just changed the amount of fencing, and I would like you to try it. So press pause and give this one a try. All right, welcome back. Let's see how you did. All right, so this time our area function in terms of x is going to be x times 200 minus 2x. So that gives me 200x minus 2x squared. So negative 2x squared plus 200x if I put it in standard form. All right, so we will have to find the vertex. Again, we have an a value of -2, which means our parabola will be opening downward, so it means the vertex will be the maximum. Makes sense because we're being asked to maximize the area. So let's find that vertex. So x equals -200 over 2 times -2, which would be -200 divided by -4, which would be 50. So this dimension right here is 50 feet. Again, either way, if you want to plug that 50 into your area function, that will help you find your area, or you can plug it in here and find the length of your rectangle. That will be 200 minus 100, which will be 100 feet, and then just multiply those two. So your area will be 5,000 square feet. If you plug it into your formula, your area formula here, you will also get the same result. So it doesn't matter which way you do it. So either way, you will get 5,000 square feet. So hopefully that kind of clears up these area problems. You can also use trajectories for targets, so rocketry, any kind of like that. In this, I used a tank round. The trajectory of a tank round can be modeled by this quadratic equation. Notice it's in meters, very important, and t is time in seconds. So make sure that you're paying attention to the labels as well. So t is time in seconds. All right, find the maximum height of the tank round. Now, in this, you will notice that my a value is equal to -4.9, which means that my parabola is opening downward. So will have a maximum height here at the vertex. So that's the first thing I'm going to need to find. I will need to find the time that occurs, though. So the time that occurs is going to be the -b over 2a. So -1676 divided by 2 times -4.9. I put all that into my calculator, and I get about 171 seconds is when that's going to happen. So if I take this function, the height function, and I plug in 171 seconds, again, and you can do that with your calculator. I would never expect my students to calculate this by hand because it's just crazy. And you get 143,317.55 meters. So you're going to be very, very high off the ground. All right, then it says find the time it takes to hit a target that is 2.45 meters off the ground. Okay, so this is a height function, right? This is a height function. So the height of my object that I'm trying to hit is 2.45 meters off the ground. So I'm going to plug that in for the height. And then solve this resulting equation. So notice the 2.45 will subtract from both sides. So you get -0 equals -4.9 t plus 1676 t. The t will divide out, and I'm going to also take out that negative. So I'm going to take out a -t, and that gives me 4.9 t plus 1676. So there is my factored form. I can use my zero product property. I will get t equals 0, which makes sense because it is leaving the ground at that time. So it's kind of doesn't make sense for what time it's going to take us to hit the target. That's when it's actually leaving the barrel. So we are going to set this second one equal to, set that equal to 0 and solve. And when you solve that, you get t is equal to, oh wait, I messed up a sign. Hold on, back up, back up. This should be a negative sign. Notice I took out the negative here, so I forgot that should be a negative. I'm very sorry I made that mistake. This is the thing, you were going to make mistakes, and it's very important that if you do make them, you be able to see them right away. I knew right away because I was calculating this and went, wait, time is negative. I can't have negative time. What did I do wrong? I messed up my signs. My number one, you guys, if you've been watching my videos this whole time, you know the number one mistake I make is I forget a sign. So I get 167 divided by 4.9, which gives you approximately 342.04 seconds. So once I fire my tank round, 342 seconds later, the target that I am at is going to explode. So that will be fun to watch. All right, so hopefully you've had enough examples of some applications of these quadratic equations. Make sure you come back next time when we talk a little bit more about some polynomials. So see you then.